Anytime working in Java, you've probably run into this classic dilemma. Should I use an array list or a linked list? Well, today we are going to unpack the hidden performance trade-offs that might completely change how you think about that question. So picture this. You've got a massive list, thousands, maybe millions of items, and you need to stick a new element right in the middle. Usually that means a whole lot of shuffling around, but what if you could just skip all of that?
Well, that is precisely the problem that linked list was built to solve. In this explainer, you're going to see exactly how it pulls this off, how it's different from an array list, and maybe most importantly, which one you should actually be using most of the time.
Okay, so to really get why linked list is such a big deal, we first need to talk about its much more common cousin, the array list, and the fundamental problem it has. The thing to remember about an array list is that, at its heart, it's just a fancy array. It keeps all of its elements neatly lined up, side by side in one big, continuous block of memory. And this structure, it's what makes it super fast to just jump to any element if you know its index. But here's the catch. Because everything has to be right next to each other, if you want to wedge a new element into the middle, well, you've got a problem. You can't just drop it in. You have to physically scoot every single element after that spot, one position over to the right to make room. And this shows you exactly what's happening. We've got our list. To get that 50 in between 10 and 20, we first have to move the 20, then the 30, then the 40. Only after all that shifting is done can we finally pop our new element into that empty space. So the big takeaway here is that the amount of work you have to do grows with the size of the list. We call this an O of N operation in computer science. Now, for a tiny list, who cares? But if your list has a million items, this shifting can become a serious performance bottleneck. So if that's the problem with ArrayList, how does linked list get around it? Well, it uses a completely different strategy under the hood. The secret sauce of a linked list is a little thing called a node. See, a node doesn't just hold your data. It's a small container that holds the data itself, but also, and this is the key part, it holds two pointers, one that points to the node before it in the list, and one that points to the node after it. So forget about that single, neat block of memory like an array list. A linked list is just a chain of these nodes. They can be scattered all over your computer's memory, all linked together by these previous and next pointers, creating a kind of virtual lineup. And this clever chain structure is the key. It lets us do that middle insertion in a totally different and way more efficient way. So how does this actually work? How does having this chain of nodes let us completely avoid all that data shifting we saw with the array list? All right, watch this. This is the magic moment. We want to put 25 between 20 and 30. We start by creating a new node for 25. Then we just do a little bit of rewiring. We tell node 20, hey, your next neighbor is now this new 25 node. Then we tell node 30, and your previous neighbor is this 25 node. And that's it. And get this, no data actually moved. Not a single element was shifted, we just updated a couple of pointers. This means the insertion itself is what we call a constant time, or O of 1 operation. It doesn't matter if the list has 10 elements or 10 million, the work to relink those nodes is exactly the same. But as they say, there is no free lunch in computer science. This amazing flexibility for insertion comes at a price, and you pay that price when you try to access elements. You see, because all those nodes are scattered around in memory, there's no way to just jump straight to, say, the 500th element. If you want to get to a specific index in a linked list, you have to start at the very beginning, at the head, and follow those next pointers one by one, until you finally land on the one you're looking for. And this right here, this is the classic trade-off. ArrayList gives you that lightning-fast O1 access by index, but it makes you pay for it when you're inserting in the middle. Linked lists gives you those super cheap O1 insertions, but it makes you pay for it every time you need to find an element by its index. Now let's zoom in a little bit, because that little asterisk next to linked lists insertion is really important. Yes, the final step of swapping the pointers is O of 1, but you first have to get to the place you want to insert, and that part is an O of N operation. You still have to traverse the list. Also, check out the memory usage. All those extra pointers in a linked list add up, creating more overhead. Okay, so the theory is great, but what does this all mean for you writing code in the real world? When should you actually reach for a linked list? Well, the textbook answer, the one you'll find in most classrooms, is pretty clear. if you're constantly adding and removing things from all over your list, and you almost never need to jump to a specific index, linked list sounds like the perfect fit. It's also fantastic if you need to build a queue, since you're only ever messing with the very beginning and end of the list. But here's where things get really, really interesting. This quote from a massively upvoted answer on Stack Overflow basically throws all that traditional advice out the window. It says that using a linked list is almost always a performance mistake. So, what gives? The answer has less to do with theory and more to do with how modern computers actually work. See, your CPU has this small, incredibly fast bit of memory called a cache, and it absolutely loves to grab big, continuous chunks of data to work on, which is exactly what an array list is. A linked list with its nodes scattered all over memory is cache hostile. It makes the CPU jump all over the place, constantly having to fetch data from slower main memory.
And this is the hidden trade-off. Modern CPUs are so ridiculously fast at copying blocks of memory that the theoretically slow O of n shifting in an array list can actually be faster in the real world than the theoretically fast O of 1 pointer updates in a linked list. Why? Because the array list keeps the CPU's cache happy and firing on all cylinders.
So what's the bottom line? It's this. Unless you are very specifically using your list like a queue, only ever adding and removing from the ends, just start with an array list. It's cache-friendly, and its real-world performance will probably blow away a linked list, even when you're doing insertions. The next time you're about to choose, ask yourself, what's really more expensive, shifting some data or a series of cache misses? The answer might surprise you.